Pluto had it coming from the beginning. Pluto's orbit crosses that of another planet. Pluto, the enigmatic small planet at the outer reaches of our solar system, is stirring up excitement in the world of astronomy. Recent reports hint at a possible encounter with Neptune, raising concerns among scientists and space fans. Notable figures like Neil deGrasse Tyson and Michio Kaku have sounded alarms about the implications of this cosmic event. But how did Pluto end up on a collision course with its neighboring planet? And what could this celestial clash mean for life on Earth? Join us as we unravel how something massive just collided with Neptune and how scientists have been left worried by this cosmic anomaly. Pluto, once hailed as a full-fledged planet, underwent a transformation in its status, being reclassified as a dwarf planet due to its peculiar orbit. Despite this demotion, Pluto still captivates and intrigues the astronomical community. Recent predictions from esteemed scientists like Neil deGrasse Tyson and Michio Kaku have raised concerns about Pluto's trajectory potentially intersecting with Neptune's, hinting at a looming threat of collision between the two celestial bodies, which could have significant repercussions for Earth. Pluto's journey around the Sun stands out due to its unique characteristics within our solar system. Its orbit is exceptionally lengthy, spanning a staggering 248 years. Since its discovery in 1930, Pluto has yet to complete a full revolution around the Sun. Adding to its mystique is the highly elongated shape of its orbit, a departure from the more circular paths followed by the major planets. Furthermore, Pluto's orbit deviates by 17 degrees from the ecliptic plane, giving its path a steeper incline compared to other planets. The combination of Pluto's inclination and its elliptical orbit introduces layers of complexity to its orbital pattern. One notable aspect is its periodic intersection with Neptune's orbit. For around 20 years during each orbit, Pluto ventures closer to the Sun than Neptune, defying expectations based on their respective positions in the solar system. Delving deeper into Pluto's orbit, it's fascinating to note that it's not a perfect circle, but rather an elongated ellipse resembling more of an oval shape. This unique orbit results in significant variations in Pluto's distance from the Sun throughout its journey. At its closest approach, Pluto comes within about 30 astronomical units, AU, of the Sun, while at its farthest point, it reaches over 49 AU away, almost twice the distance of Neptune from the Sun. Moreover, Pluto's orbit is inclined at an angle relative to the orbits of the major planets in our solar system. This inclination not only contributes to the complexity of its orbit but also plays a crucial role in its interactions with other celestial bodies, particularly Neptune. When Pluto crosses paths with Neptune, their gravitational tugs influence each other, altering their trajectories over time. The intricate dance between Pluto and Neptune underscores the dynamic nature of our solar system. While Pluto was once considered a lone wanderer in the outer reaches, its close encounters with Neptune highlight the interconnectedness of celestial bodies, each exerting gravitational forces that shape the paths of others. In recent years, advancements in observational technology have allowed astronomers to track Pluto's movements with greater precision. This has led to a deeper understanding of its orbit and its potential implications for the stability of the outer solar system. The likelihood of a direct collision between Pluto and Neptune remains low, but the possibility cannot be entirely discounted, prompting continued monitoring and study by the astronomical community. Despite its diminutive size and distant location, Pluto continues to command attention and curiosity among scientists and enthusiasts alike. The question arises, why hasn't there been a crash between Pluto and Neptune? The answer lies in the pull of gravity from other planets. Astronomers began studying Pluto's path soon after finding it, and its route puzzled them. Unlike most planets that stick close to the same plane as they orbit the Sun, called the ecliptic plane, Pluto stands out with its steep angle and oval-shaped orbit. The mystery deepened when they realized Pluto's path crossed Neptune's. Despite these complexities, Pluto's orbit remained stable, showcasing the intricate mechanics of space. Understanding how three celestial bodies move and interact gravitationally, like Pluto, Neptune, and the Sun, is a big challenge. It's like trying to predict where they'll go based on where they start and how they pull on each other. For Pluto, this challenge reveals how its path, Neptune's path, and the Sun's pull all work together. Terms like azimuthal libration, latitude libration, and the VZK oscillation help scientists solve this cosmic puzzle. Azimuthal libration is crucial for keeping planets in their orbits. When Pluto crosses Neptune's path, it's at least 90 degrees away, keeping them from crashing. Latitude libration makes sure that when Pluto nears Neptune or other big planets, it's well above their path, reducing the chance of a collision. The VZK oscillation, named after scientist von Zippi, Leo, and Chi, explains why Pluto's orbit seems strange but stays steady over time. Despite the chaos in space, even though space seems random, some patterns and rules keep things in order. These rules keep Pluto's orbit stable, preventing crashes with Neptune or changes in its path. The idea of orbital chaos, showing how a celestial body's path is very sensitive to where it starts, is well illustrated by Pluto. Even small changes in its position or speed can mess up its orbit over a long time. Scientists use computer simulations to figure out how Pluto moves in space. These simulations use fancy math to copy how Pluto interacts with other space stuff, like Neptune. By tweaking these simulations just a bit, astronomers can see how tiny changes can change Pluto's path. In the late 1980s, these simulations found something interesting about Pluto's orbit. Even though there are things that should make it stable, Pluto's orbit can still be unpredictable. Just a tiny difference in where Pluto starts or how fast it's going can make big changes over many years. But even with all this chaos, Pluto's orbit stays stable for a super long time, like billions of years. This suggests that even though Pluto looks all over the place, its journey around the Sun follows some sort of order. Predicting what'll happen with planets like Pluto, which have wonky orbits, is hard. These systems are so unpredictable that it's tough to guess what'll happen in the long run. Simulations help us get an idea of what might happen, but they also show us that we can't predict everything perfectly. These models need exact starting points, and they simulate complicated stuff. Even a tiny mistake can lead to totally different results, which makes it hard to make accurate predictions. Understanding Pluto's orbit is important, especially when we think about whether it might crash into Neptune in the future. This knowledge helps us understand better how our solar system works. Pluto's orbit shows us how orbits that seem wobbly can balance out because of gravity and how things move in space. It's important to keep watching and studying these things so we can understand where we fit in the universe. When we explore space, we find out that things can be unpredictable, and Pluto's orbit is a great example of that unpredictability. Pluto's orbit is not like those of the other planets. It's more oval-shaped, which means it's not a perfect circle. Sometimes it even gets closer to the Sun than Neptune does. This can make things tricky because Neptune is also out there cruising along its path. There's a small chance that Pluto and Neptune could bump into each other at some point. Despite its odd orbit, Pluto manages to keep its distance from Neptune most of the time. This is because of something called gravitational forces. Gravity is like an invisible force that pulls things toward each other. So even though Pluto and Neptune might seem like they're on a crash course, their orbits are carefully choreographed dances guided by the pull of gravity. Pluto's orbit teaches us that space is full of surprises. What seems chaotic at first glance can be a delicate balance of forces. By studying Pluto's orbit, scientists gain insights into the intricate mechanics of our solar system. This ongoing observation and analysis are essential for expanding our knowledge of the universe and our place within it. Imagine if Pluto and Neptune did collide. It would be a cosmic event, sending shockwaves through our understanding of the solar system. While we've made progress in understanding space, Pluto's situation shows that we still have a lot to learn. Studying how big planets affect Pluto's path gives us important clues about how our whole solar system works. It shows us that where each planet is and how it moves can change the paths of other things in space. Even though space is complicated, some top scientists are worried that Pluto might crash into Neptune. This makes them wonder why this might happen even though it seems unlikely. Neil deGrasse Tyson, a famous space scientist, has some interesting ideas about Pluto. He thinks that reclassifying Pluto as a dwarf planet, not a big one like Earth, is a step forward. He believes we're always learning new things about how things move in space. Tyson sees Pluto's weird path as a sign that there's still a lot we don't know. He thinks that the mysteries of space are what make studying it so exciting. He also knows that big events in space, like Pluto's reclassification, get people interested in astronomy. Tyson wants to help people understand the cool and sometimes weird things about how space works. He thinks it's important to talk about how space mechanics can surprise us. Tyson works with other scientists to warn people about the possible dangers of Pluto's strange path. After studying Pluto a lot, he's worried that it might crash into Neptune one day. He says this could cause big problems for our whole solar system. A crash between Pluto and Neptune would be a rare and serious event. It would release a lot of energy and could break apart Pluto. Pieces from the crash could fly around space and hit other planets and moons. Neptune might also feel the impact and change how it moves. Renowned theoretical physicist Michio Kaku, known for his contributions to string theory and science communication, offers an intriguing perspective on space exploration. He believes understanding the future of space travel and the link between celestial mechanics and theoretical physics can be gleaned from studying phenomena like Pluto's orbit. Kaku sees Pluto's orbit as a window into the future of space exploration. By grasping the intricate gravitational interactions and orbital dynamics of celestial bodies like Pluto, we can enhance future space missions, aiding in safer navigation through the solar system, predicting potential risks, and planning missions to distant corners of our cosmic neighborhood. Kaku emphasizes that lessons learned from Pluto's orbit can be applied to exploring other celestial bodies, providing a roadmap for understanding distant worlds. He often highlights the deep connection between celestial mechanics and theoretical physics, stressing that the movements and interactions of planets, such as the gravitational dance between Pluto and Neptune, are rooted in fundamental principles of physics. Kaku's work in theoretical physics, especially string theory, aims to unravel these principles at their core. He suggests that studying the complexities of celestial mechanics, like Pluto's orbit, can offer insights into the underlying laws of the universe. Similar to Tyson, Kaku has also contemplated the potential collision of celestial bodies, relating it to his theories about the universe. A collision between Pluto and Neptune, while significant in astrophysics, could offer a unique observational opportunity, potentially contributing to our understanding of string theory. String theory, which replaces point-like particles with one-dimensional strings, seeks to describe the fundamental forces and matter in the universe. Such a collision could create extreme conditions of energy and gravity, shedding light on the behavior of fundamental particles and forces under extreme circumstances, a key focus in string theory. Moreover, the gravitational waves produced by such a collision could provide valuable data for testing predictions of string theory concerning gravity and spacetime. While the direct impact on Earth would be minimal due to our distance from the outer solar system, the scientific implications could be profound. Understanding events like this could deepen our comprehension of the fundamental nature of the universe as described by string theory and other theoretical physics areas. Its unique characteristics influenced by the gravitational forces of neighboring planets, particularly Neptune, highlight the intricate and dynamic nature of space. Yet, the universe holds many mysteries, and the three-body problem is just one of them. Scientists anticipate other potential disasters, underscoring the ongoing quest for understanding and exploration in the vast cosmos. Although it's highly unlikely, there's still a small chance of planets bumping into each other in space. This can happen because planets' paths are affected by different things, like gravity from other planets, which scientists call the three-body problem. In places like the TRAPPIST-1 system, where there are 7 Earth-sized planets, the gravitational forces create a sort of rhythm in how the planets move, called orbital resonances. Over time, these patterns can make a planet's path less stable and could lead to collisions. Even though systems like TRAPPIST-1 are busy with planets, collisions aren't happening right now. Scientists keep a close eye on these systems to understand how planets affect each other's paths, especially when they get close. This helps us understand how planets move in space. Sometimes there are rogue planets, which don't orbit a star and float around unpredictably. These planets used to be part of a star system but got kicked out due to things like gravity or when another star came too close. Over time, these wandering planets can travel far and might run into other star systems. But because space is mostly empty, the chance of them hitting another planet is very low. Rogue planets are rare compared to the number of stars and planets with stable orbits, so collisions are even less likely. When galaxies merge, it can mess up the orbits of the star systems inside them. Although planets probably won't smash into each other directly during these big events, the strong gravity can change how stars and planets move. Sometimes planets get flung out into space, becoming rogue worlds. Other times, they might crash into each other or their host stars. These disruptions could even create new celestial bodies or make new stars. The late heavy bombardment theory suggests that around 4 billion years ago, there was a time of increased crashes involving comets and asteroids. This surge in impacts is believed to have happened because the outer planets like Jupiter and Saturn were moving around a lot, which messed up the paths of lots of smaller objects in space. As a result, these smaller things got thrown onto unpredictable paths, many ending up in the inner part of our solar system. This led to a big increase in crashes on planets like Earth. While these collisions didn't involve planets crashing into each other directly, they showed how gravity can make big changes to how things move in space. Scientists think this bombardment shaped the surfaces and histories of planets in our solar system. It might have even brought water and organic stuff to Earth, helping shape our planet. As stars change over time, they lose mass, which can affect the paths of planets around them, sometimes causing them to widen and potentially overlap. This change is most noticeable in systems where stars are nearing the end of their life cycle. As a star ages and uses up its nuclear fuel, it undergoes significant mass changes, especially during stages like the red giant phase or when it releases material in a planetary nebula. These mass variations can greatly affect the gravitational balance of the system, causing nearby planets' orbits to either move outward or become more compressed. This phenomenon is more common in systems with multiple stars, where complex gravitational interactions can lead to unstable orbits. In such systems, the gravitational forces from multiple stars can interact unpredictably, making orbital shifts more likely and increasing the chances of orbits intersecting. This could lead to situations where planets are captured by another star, collide with other celestial bodies, or even get ejected into interstellar space. Although the actual likelihood of a planet collision is considered highly improbable due to the vastness of space and the relatively small size of celestial bodies, these possibilities are of great interest to astronomers and astrophysicists, as they provide insights into the dynamics of planetary systems and the evolution of galaxies. The ongoing exploration of Pluto's orbit exemplifies the continuous quest for knowledge in space.